Good afternoon. I'm sorry about the slight delay in getting going. We're having some technical difficulties with the share. It seems it didn't like Safari as much as it likes Chrome. Uh, right. So let's begin again. I have started this once already today, but the connection wasn't working. Welcome, and what I'd like to talk about this afternoon is the rationale for continuous delivery. And really kind of my argument is that software development is sorry, we've got a bit of an echo going on. Just a sec, excuse me. Hello? Cool. Sorry about that. Okay, let me start again. So my argument is that software development is one of the more difficult things that we as human beings do. As an industry, our history hasn't been one of real success. If you look at the history of software projects, on the whole, the story is not really very good. You can take these sorts of software project surveys with a degree of skepticism, and I think that's an appropriate approach because they're not scientifically rigorous. I can't compare my software project to your software project because there are so many variables involved. There are so many differences, our choice of technologies, the experience, the sorts of projects that we've worked on before. All of these sorts of things come into play and have an effect on how well we're going to do at making our projects work. But on the whole, even so, even with that non-rigorous nature of these sorts of project surveys, they tend to tell a consistently poor story of software project success. This last one is kind of funny if it wasn't so serious. In a study of nearly 6,000 large-scale projects, 17% of the projects go so badly that they threaten the existence of the company performing them. So I would argue that our history of software projects is not really great. If software projects worked, if they were a normal thing, what we'd expect to see is a curve like this. We'd expect to see as many software projects that finished ahead of time, ahead of budget, below budget and delighting their users as we saw behind time, over budget and disappointing their users. But that's not really what we see. What we tend to see, I believe, is more like this. And I think that what's happened is that we've grown up and our industry to assume that this is what normal looks like for software projects. I believe that's not necessarily the case, and I hope to convince you that I'm right through the rest of this presentation. So I'd say that software development on the whole has kind of been suboptimal. But I think that there are signs of change. I think that there's hope. And I chose this picture carefully. This is not a perfectly formed production quality machine. This is something that somebody's put together as a one-off, and I think that's part of what good looks like at the moment. We don't have a clear cookie cutter approach to software development. It's going to be tailored and refined to each individual circumstance. But we do know some things that clearly work. And I want to describe some of those things this afternoon. So what have we tried? Well, we've tried looking at other industries and learning lessons from them. We've tried waterfall approaches to managing our projects, V models. We've tried decomposing the problem into chunks and building siloed organization and passing ideas through these different silos on their way to production. We've tried more iterative approaches to software development. We've tried using Scrum and Agile processes to cope with the project management aspects. We've tried extreme programming to cope with the engineering challenges of developing software. We've tried hiring really smart people and putting them in a corner somewhere. And we've tried hiring young smart people and putting them in the corner because they're a bit cheaper. and we've tried hiring young, smart people in foreign countries because they're even cheaper. And all of these things have some role to play, but none of them are really the whole answer. Part of our difficulty as an industry comes down to this document. This is the document that originally coined the term waterfall development in the context of software development. This is Dr. Winston Royce's original paper that described waterfall for the first time as a process. This was written in 1970 and was submitted to an IEEE conference. The famous diagram that describes software development as a waterfall process, it comes on the second page, and this is the diagram. I'm pretty certain that everybody watching this will have seen a version of this diagram at some point in their careers. You might have been taught this as a software development process. You might have seen it as part of the processes in organizations that you've worked in, or you just read about it as a strange thing that other people do. But I'm fairly sure you will have seen this picture. What you probably haven't seen before, what kind of surprised me when I looked into it, was the next paragraph. And I've kind of blown this up so it's easier to read. So this next paragraph says, the implementation described above is risky and invites failure. The testing phase, which occurs at the end of the development cycle, is the first event for which timing, storage, input-output transfers, and so on are experienced as distinguished from analyzed. These phenomena are not precisely analyzable. So what Dr. Royce was trying to do in his paper was say, don't do it like this. Don't implement a waterfall approach. And apparently, I've heard that he spent much of the rest of his career telling people, that's not what I meant, and I don't do that. So we as an industry, we've suffered from a naive approach to process and applying that incorrectly to solve problems. Now, why did that happen? Well, it's kind of easy to imagine that first diagram that I showed you, just remembering that and going home and drawing that on a whiteboard or on a piece of paper and describing it to your teams when you got back from the conference. This is the diagram that Royce was actually recommending. And this is a harder diagram to remember and to carry back to your teams to inform them of what it is that you should be doing. So this one wasn't quite as popular. Looking at this with the perspective of 21st century hindsight, it's kind of there are some really interesting things in here. It says that testing must be planned, controlled, and monitored. It says do the job twice if possible. It says involve the customer. Crucially, in this diagram, it includes these feedback loops. It says that there should be a link back from testing into program design, and from program design back into requirements. I think if you take a generous view of what this is trying to describe, this is really trying to describe an iterative approach to software development, maybe even an agile approach to software development. This was in 1970, so it's fairly clear where we went wrong. We just misapplied what it was that Dr. Royce was trying to describe to us. Here's a picture of a quayside in the west of Ireland. And if you look carefully in the bottom left-hand corner, you can see that somebody's been unfortunate enough to drive a car off the quayside. So what do you do if you drive a car off a quayside? Well, you go and get a crane. But then maybe that doesn't work so well. What do you do now? Well, we've got the car out, and now we'll try and get the old crane out, and that goes badly too. Einstein said insanity is doing the same thing over and over again and expecting different results. So if our software development process is not really fulfilling our needs, we should be looking to do something different. If it's really not working, we should be looking to do anything different. We should be trying different things to find out what works. So what is it that we really want? If we go back to first principles, what is it that software development is really all about? I would argue it's this, and I would argue that any organization that creates software is really looking for this. We want to have an idea, We want to get that idea in the form of working software into the hands of our users, and we want to figure out what our users make of that idea. And I think whatever the nature of the software, this is really what it is that we are employed to do. This is really what software development is all about. So I want to pose a question. So what's the most successful invention in human history? And here are some pictures that are intended to mislead you into the answer towards that. So I would argue that without too much fear of contradiction, science is the most successful invention in human experience. All of these things that I've shown you, all of the things that you can think of, pretty much all of the fruits of 20th and 21st century innovation are as a result of science. And by that, I don't mean large hadron colliders, gravitational wave detectors, modern medicine, any of those things. What I mean is the scientific method, the simple process, the empirical approach of not really trusting our guesses and trying to figure out a way to avoid guessing and to be more deliberate in making decisions and learning. So, like all good presenters, I went and looked up on Wikipedia what it said the scientific method was, and this is how it describes the scientific method. It says that we should make a guess based on experience and observation. We should propose an explanation for that guess, and we should make a prediction based on that explanation, and we should test the prediction and see whether it meets our expectations, and crucially we should then repeat. This is the most powerful problem-solving technique that the human species has evolved. This underpins all of science. This underpins all of the amazing things that we have done as a species. If software development is genuinely one of the more difficult things that we as a species undertake, and I believe it is, I think it takes creativity, technical intelligence, technical sophistication, great teamwork, all sorts of aspects of behavior that stretch us as human beings. It takes all of those to do good software development. Then shouldn't we be applying, if it's really that difficult, shouldn't we be applying our strongest problem-solving technique? Shouldn't we be using a more scientific approach to solving these sorts of problems? So let's look at a little bit more data about projects. So here's some data from a source called the Chaos Manifesto. This has been published by the Standish Group for many years now. And on the whole, they pretty consistently say that agile approaches, that is iterative approaches to software development, work better than waterfall approaches. Many people think that that work is a little bit too pessimistic. And one of those people is Scott Ambler, and this is my representation of my organization of his data. So he's a little bit more generous towards the success rates of traditional approaches to software development. It kind of amused me the first time that I read this data that if you make up on the spot, that is an ad hoc approach to this process, if you make your process up on the spot, that's slightly more effective than the waterfall approach. But that aside, the top line is really where I'd like you to kind of focus your attention. These are iterative approaches to development. These are establishing this kind of feedback loop that allow us to learn and adapt as we move forwards. Lean in particular stands out as the most effective at producing successful results when we apply this approach. So what's that about? So lean thinking comes from the work, really initially the work of Edwards Deming after the Second World War, who went to Japan and revolutionized their industry and made Japan, the Japanese economy, the powerhouse that it became through the latter half of the 20th century. And lean thinking, Deming's ideas at the time were really very much in line with my arguments so far, in that he went and looked and said, well, this is a difficult problem. Manufacturing and industry and production is a difficult problem. So how should we apply a rational approach to this? I know, let's apply the scientific method. So he took the scientific method and applied it to process, in his case, manufacturing and production processes, and kind of distilling the thinking and the outcomes of that developed into lean thinking and the Toyota method and so on. This is kind of a synopsis of that. So we want to deliver quickly. We want to be able to learn from what we do and iterate. We don't want to invest too much upfront work in the things that we do. We want to focus, have a very laser beam focus on quality. We want to make sure that we're building quality in from the outset and not trying to fix things later, because that slows us down and gets in the way of us delivering quickly. We want to look at the whole process. It's no good us shaving 5 minutes off our build or our test execution if it takes us 5 weeks to determine which stories to run or which pieces, which ideas are valuable to our users. We want to look to eliminate waste. We want our approach to be efficient and effective. And waste can take various forms. It can surface in unnecessary variations where we do the same thing in different ways. I once worked on a project that had 5 different persistence mechanisms. That's clearly a waste of a kind. Waste also exhibits itself as overburden. If as a team we're trying to do too many things, we will go slower. And so the way to speed up as a team is to do less stuff, is to take on less, and to make sure that we can work optimally and effectively and efficiently. And the last one of these is wasteful activities. The worst thing that we can do is work very hard on something that doesn't really matter. Writing documents that people never read, creating features that users never use. All of these things play into this idea of waste in our approach to software development. We need to amplify learning. We want to make sure that as a team, we are learning and evolving and improving all of the time. Modern lean thinkers talk in terms of actually optimizing your process to prioritize learning against all other things. You aim to learn, and as a second order effect, you get good productivity. You develop more features and higher quality as a result of aiming to learn. We want to make decisions late. If we make all of the key decisions for a project before we start doing any work, then we're actually making those decisions at a point in the life cycle of the project when we know the least that we will ever know about the project. We know the least about the way that the team's going to work together. We know the least about the technologies that we're using. We know the least about what users are going to want of our software. And so deferring decisions until the last responsible moment is a much more effective way of making higher quality decisions. And finally, in order to do this, we want to empower the team. We want the people that cause a problem to witness the problem, because they are going to be the best placed people to fix a problem. And so we want development teams to be responsible for the software when it's in production. We want them to be able to perceive what's working and what's not. We want them to be able to understand what the implications are for operators who are seeing the software work in production. We want them to understand what it means to the users to use the software that they're creating, and what's the value that they get out of it. And so this is all about ensuring that the team are both in the right place to be able to witness these things, but also have the power to be able to change what they do and work in different ways to address any problems that arise. In summary, I think that what we're really talking about is to try and do this. We're trying to establish a series of feedback loops. At the outside of this picture is the one that I mentioned before. We want to optimize the feedback loop from having an idea to getting valuable software into the hands of our users and figuring out what they make of it. That's the feedback loop that businesses have been demanding of us as software professionals from the dawn of the software industry, really. And to be honest, on the whole, we haven't really fulfilled that demand. That's what they want. They want to be able to turn their ideas around quickly and efficiently and learn as they go. At the inside of this loop, is the very short feedback loop of test-driven development. We want to write a test and see it fail. We want to write some code to make the test pass. We want to refactor that code and tidy it up. We want to commit the change, and then we want to move on to the next test. And in between, there are other feedback loops. That once you start thinking this way, there are many more feedback loops than this to look for. This is part of that empirical, scientific, more engineering approach to software development. We should be looking to establish these feedback loops in everything that we do. We should be looking to establish the feedback loops in the way that our teams work, in the way that our processes work, making sure that we're doing retrospectives to reflect on our processes as a team and how to refine them, as well as the more technical ones, which I'm showing in this diagram. As you may have guessed from my presentation so far, I'm kind of a bit of a popular science nerd, and I enjoy, I'm interested in physics and so on. This is Richard Feynman, who's one of my heroes. He's a Nobel Prize winning physicist. Feynman came up with the theory of quantum electrodynamics, which is the most accurate predictive tool that human beings have ever invented. I think it's 3 orders of magnitude more accurate in its predictions than general relativity, which is no mean theory in its own. Feynman was a genuine first-class genius. He's one of the finest minds that humanity has ever created. And in addition to all of those things, he was also something of a philosopher on science and a great source of quotes if you're ever looking for one around the subject of science. And this is one of my favorite quotes. And remember, this is Feynman, a genuine genius, saying this. It doesn't matter how intelligent you are, if you guess and that guess cannot be backed by experimental evidence, then it's still a guess. So we need to find a way of eliminating the guesses from the way in which we work. We need to find a way of working in a way that allows us to evaluate our predictions and learn from them and move forwards. Now, continuous delivery is really grounded in this more experimental, empirical approach to problem solving. And the other dimension to that is this idea of cycle time. And we are enormously fortunate to have come up with this notion, this ruler, this benchmark, this metric that allows us to evaluate how well we're doing. It's my argument that if you work to optimize cycle time is the idea of, if you imagine the smallest possible change that you can make to your production system, and that change going through all of the normal evaluations, processes, handoffs, documentation, testing, whatever it might be, on its way to production that any other change would go through, how long would it take you to do that change? And I'm going to show you 2 cycle times from projects that I worked on. So it's my argument that if you work to optimize your cycle time, that is, reduce it, then you will drive out all of continuous delivery, all of agile theory, all of lean theory, as a consequence of doing this. You can't have a short cycle time if you don't have a great story on automated testing. You can't have a short cycle time if you work in large teams. If you can't have a short cycle time if you're handing changes between different silos in teams. And so it kind of brings out the need for practices like DevOps community promote. You can't have a short cycle time if you don't have a great story in terms of configuration management and environment setup and deployment. All of these things fall out as a consequence of working to reduce your cycle time. So this first cycle time that's on the screen now is from a project that I worked in many years ago for one of the large banks here in the UK. This bank couldn't release any change to their software system in under 103 days. Now, if you have a cycle time of 103 days, you don't really have any feedback loop. If somebody comes to me after 103 days and says, Dave, you've just broken production, I'm going to say, I don't know what the change was. Are you sure it was me? Maybe it was somebody else. Maybe I was on holiday that week. I don't know. But I'm certainly not going to remember what it was that I was working on 103 days ago. It's not going to be at the forefront of my mind. It's not going to be simple for me to figure out what the failure might be. Worse than that, if you've got a cycle time of 103 days, that means that every 103 days, you're going to be releasing a lot of changes together. So maybe it wasn't my fault that production is broken. Maybe it was the combination of my change and somebody else's change interacting in ways that we didn't anticipate. If you've got a 103-day cycle time, you just don't have a feedback loop. This is a cycle time from a second project. Interestingly, this was a significantly more complex project. The first project was kind of one component of about 15 or 20 components in the second project. And yet the cycle time for this project was 57 minutes. We could evaluate any change to our software system in 57 minutes. We once decided that we didn't like the commercial terms that we had with our database vendor, and we switched our database vendor out. We made the changes to the code. We ran the code through a battery of tests through our and got a result. The first time we did that, we got some failures which pointed to things that could fix, and then we fixed those problems, ran the tests again, and in 57 minutes we got a result. Everything had passed, and so we were happy to release this change into production. I've worked on projects where that change alone would have been a 6-month project, but we could do it in this case 2 lots of 57 minutes because we did have some test failures the first time. Cycle time is a wonderful tool, is a wonderful metric. As a consultant, I often advise my clients to start off by measuring their cycle time, and then at whatever stage you're at, look to reduce it. The act of aiming to reduce your cycle time will drive out good behavior. It's not automatically going to just work, but what it's going to do, it's going to highlight problems. If your configuration management is poor, it's going to, if you try and release more frequently, it's going to show that up and you're going to have to fix those problems. If your automated testing is poor, it's going to highlight that problem and you're going to have to improve in that area. Cycle time is a wonderful metric that allows us to focus on the things that really matter in software development. So what are we really talking about when we're talking about continuous delivery? Well, first up, if you look at the Agile Manifesto, continuous delivery is the first property of Agile development. So the Agile Manifesto says our highest priority is to satisfy the customer through early and continuous delivery of valuable software. This is going back again, have an idea, get that idea into the hands of users, and figure out what our users make of the idea. So it's the first principle of the Agile Manifesto. It's also kind of the logical extension of continuous integration. Continuous integration is a great practice for development teams. It allows teams to understand as they're going the impact of their changes. Continuous delivery just takes that idea further, both upstream and downstream of the continuous integration process, and looks holistically at software development approach. Which brings me to my next point, which is that this is a holistic approach. This is about all of software development. If we are genuinely looking to optimize the process from having an idea to getting valuable software into the hands of our users and figuring out what they make of it, that encompasses all of software development. It means that we need to think about the way that ideas flow through the business, our development organization, how we test, how we deploy software, how we operate it in production. All of these things are impacted by this approach. A good mental model for this is to imagine that every time that we commit a change, we're giving birth to a release candidate. And the job of our continuous integration and continuous delivery system is to evaluate these release candidates and prove that they're not fit to make it into production. I purposely said it that way around because this is the idea of falsifiability. We can never have enough tests to prove that our code is good. But as soon as we have one test that fails, we know that that code is not good. And so we can use our automated testing to falsify release candidates. As soon we can build in mechanisms that prevent us from deploying release candidates into production that have failed any tests. This gives us a high quality threshold and a rigorous approach, a high disciplined approach to the approach to software development and release. When people look at agile processes like Scrum, there's often a lengthy discussion about what the definition of done is. I would argue that we're never done until our software is in the hands of our users delivering value. That's what done really means, and that's what we should be aiming for. We should be aiming to get value into the hands of our users, and that's what done really means. If we release software and our users aren't using it and it's not delivering value, we're not done. If we release software and we get it to the point where it's usable but is not yet deployed into production, we're not done. If we release software that fails some tests and is not deployable, we're not done. So we should be focusing on valuable software in the hands of our users. So what does this really mean? So we're trying to create a repeatable, reliable process for releasing software. If we want the process to be repeatable and reliable, unfortunately, that kind of rules us out. Human beings are not really very good at repeatable and reliable. As one of my good friends said, human beings are no good at for loops. We're not good at doing things over and over again and in a consistent way. We're particularly not good at doing technically demanding, complex, repetitive tasks in a reliable way. We'll have a coffee break and come back and forget where we were and miss a step or misread instructions, all of these sorts of things. If we want repeatable and reliable, we need to look towards automation. We need to automate almost everything. Machines are wonderful at being repeatable and reliable. And so we should look to automate nearly everything. We should automate our testing, we should automate our configuration management, we should automate the deployment of our systems into test environments and into production as far as we possibly can. If we want to automate nearly everything, then we need to keep nearly everything under version control, not just the source code of our software, but its configuration, the specification of the environments that it works in, the things that it depends upon. All of those things need to be precisely defined and configuration managed. A good test of this kind of idea is to imagine going back and deploying the version of your software that was running in production 6 months ago into a test environment. If you could completely recreate that version of that software in a test environment at the push of a button, then you're doing a pretty good job of version control. If you can't do that, then why can't you do that? What's lacking? What specification? Why can't you recreate that entire environment in a test environment? Software is an unusual thing in human experience. Most of human experience, if we do something and it's difficult or painful, it probably makes sense to avoid it and to steer clear of it. In software, if we do that, things are only going to get worse. If you're releasing software and the release process is an unpleasant experience and you're doing it once every 6 months, the worst thing that you can do is to decide to start releasing once every 12 months instead. It's going to get more difficult, more fraught with pain and complexity if you're doing it less often. Instead, if you're releasing every 6 months and that's difficult, start releasing every 3 months, start releasing every month, start releasing every week, every day, every hour, every 57 minutes. Work to optimize that cycle time and reduce it as far as practical. Again, another good mental thought experiment for this is imagine being in the situation where something bad is happening in production, and you've got to deploy a fix into production. In an ideal world, wouldn't you love to be able to run all of the tests before you deploy the fix at the point at which your software is broken? This is not really one of the points at which you really want to take more risks. You'd rather take fewer risks. And so if you could have a cycle time that was so short that you could afford to run all of the tests again and just automatically deploy the fix once you'd proved that it worked into production, wouldn't that be a wonderful place to be? If we want to do all of these things, then we need our software to work in deterministic ways. We need it to be consistent in the way it's deployed and operates, and give consistent results to tests, and work in the same way when we deploy it each time. So we need to be focusing on quality and driving quality throughout our design processes, not just for the source of the code that our users will experience, but also for our tooling, our configuration management, our tests. All of those things need to be high quality and rigorous in their approach. I've kind of talked about this. This is really shorthand for in the hands of our users delivering value. We're not done until we're doing that. Software is increasingly in the 21st century foundational to the way in which organizations work. Across the board, software is driving innovation and disruption in virtually all industries. I was talking to a friend in the automotive industry recently, and they see, to a large degree, they see cars as transporters for software. There are millions of lines of code in a modern car. And it's only growing as cars move towards autonomy. This is true across the board for all industries, and so if you think about that, if you think about the implications of the importance of software to modern commercial organizations in particular, then what that means is everybody has a stake in the changes that are flowing through software development process. We need to have these ideas. We need to get them implemented and in a high quality manner and out into the hands of our users quickly and efficiently to figure out what they make of them. And everybody has a stake in that, whether they're working in operations, development, testing, the business. All people are interested in what's going on, because this is fundamentally to do with what the organization that you work in is. That software is kind of the defining characteristics, the differentiator for most organizations these days. And if you want to do all of these things, this is not the sort of process where you hire a consultant or buy a book or attend a training course and it's all done. This is a change in approach. This is an approach that works differently to what we thought software development was before. This is about working more empirically, more iteratively, working in high-functioning teams that have control over their own destiny. And these teams need to be looking at every aspect of their work and looking to improve on a continuous basis. If you look at the best software development teams in the world, this is the outstanding hallmark of those teams. They are never satisfied with what they're doing now. They're always looking to improve. They're changing the software, they're changing the testing approach, they're changing their tooling, they're changing the process, they're changing the teams themselves, the dependencies between them, and always experimenting and trying new things to figure out what works more efficiently. This quote is really just me showing off. So if software development was the opening act to a great performance, continuous delivery is the headliner. This is really what we've been looking for in software development for many years. We've been looking to get this optimization of the process from idea to value in the hands of our users. So let's dig a little bit more deeply into one of the kind of the foundational ideas of continuous delivery, the idea of the deployment pipeline. The deployment pipeline is a machine for evaluating release candidates. So if we think of our software development process as this holistic thing, and we want to automate as much of that as possible, the deployment pipeline is the embodiment of that automation. So we start off with some developers working on some changes, and they're going to commit those changes when they think that they're ready to some version control system. That in turn is going to trigger an evaluation of those changes. This stage we call the commit stage, and what we're looking at this point is that we want very fast feedback. We want the people that have made the change to understand the likely implications of their change as quickly and as efficiently as we can achieve. Ideally, we're looking for around about a 5-minute feedback cycle at this point. So we'd like to be able to give the results back from the commit stage to the developers in about 5 minutes. What I've described so far is really just continuous integration. This is pretty much what continuous integration is. From here, we kind of start to diverge and extend the reach of continuous integration further. If the commit stage is one of the reasons why we want the commit stage to be fast and efficient is we want the developers to be in a position to fix problems quickly. We want to fail fast. That's the best way that we can have the changes that the developers made fresh in their minds, so that in the event of a failure, they're going to fix them really quickly or efficiently. If the commit stage passes, the developers can move on and start working on something new. Meanwhile, we want to store the results of a successful commit stage. What we want is that we want to generate the release candidate that will be deployed into production. Now, what we've just done is that we've just probably run, for a software project of any size, we've probably just run tens of thousands of very fast and efficient automated tests. So we've just tested a particular build of the software. We don't want to rebuild again, because maybe we would rebuild with a different version of the compiler or link with different libraries or do something else silly that would invalidate those results. Maybe those tests would have found a problem if we'd run them again with a different compiler version. So what we want to do is, if we've built the software once and evaluated it now, that is the version of the software that we will ultimately release into production if this release candidate makes it that far. So we want to store the fruits of that build, the results of that build, the binary artifacts that will be deployed into production, and we want to store those, and the rest of our evaluations will be carried out on those. So we won't rebuild it. That has some implications of its own. It means that we can't afford to bundle together the configuration of our software with the deployable artifacts, the runnable pieces itself. We need to separate the configuration from the binary artifacts. So we're going to store in our artifact repository things like jars, .NET assemblies, RPMs, YUMs, whatever the deployable unit of your software may be. That's the stuff that we're going to store and in our artifact repository. Now, there are few stronger proponents of test-driven development than me, and the commit stage is largely made out of unit tests that are the fruits of test-driven development. What test-driven development does, though, is test-driven development asserts that the software does what the developers think the software should do. That's not necessarily the same as asserting that the software does what the users need it to do. And so we need a different form of evaluation, a different form of test, a different form of automated test to assert that the software does what the users need it to do. In continuous delivery parlance, we call these acceptance tests. These are not manual user acceptance tests, these are automated acceptance tests. It's my argument that you shouldn't waste human beings on manual regression testing of any kind. Human beings are great for different sorts of different things, but as we've already discussed, repeatability and reliability, which is what you need from a regression test, isn't one of the things that people are good at. So for that, we want to automate. So we want to automate our acceptance tests. We're going to wait for the acceptance test environment to come free. We're going to go and look in the artifact repository for the newest release candidate that's been successfully committed. We're going to deploy that release candidate into a test environment, and then we're going to run a series of black box tests in a production-like scenarios, in a production-like deployment of the software to evaluate that the software does what the users want it to do. If all is successful or not, we'll tag the release candidate with the results of the acceptance test. Now, I've already described that human beings are no good at regression testing, but they are good at some forms of testing that automation is not good at. If I write a web page that has a blue button with blue text on the button, an automated test will happily go and press the button. A human being is going to say, I don't know what that button's for, and either decide to press it or not, but they're not going to know what it's for. They're going to have a different response. So for some sorts of things, you want human beings to do exploratory testing. You want them to wander around the software, try different crazy things that you would never write an automated test for. This is the sort of testing that you do once and only once. Any form of testing that you want to repeat over and over again should be automated. Exploratory testing is valuably done by people. So here we're going to provide some tools that will allow us to deploy the selected release candidate, deploy it to a test environment, allow the users to interact with that system, and tag the release candidate with the result of their testing. This example was based on a high-performance, low latency trading system. We took performance of our system very seriously. It was a business critical aspect of the behavior of our system. And so we divided performance testing into two different stages. So we would do component performance testing. We would test the thresholds of performance for certain components in the system, and we would do whole system performance testing, where we would do lifelike scenarios of interaction with the whole system deployed on exactly the same hardware as we would see in production, so that we could evaluate load and so on of our system. By this time, if you think of all of the testing that's gone on, we've looked at the commit stage, and we've got a good understanding that the software does what the developers think it should do. We've run the acceptance stage, and we've got a good understanding that the software does what the users want it to do. We've evaluated it from the point of view of a human being. Does the software paint pretty pictures in the heads of a user of the software, and is it understandable? Can they anticipate where it's going next and what to do with it next? Those sorts of things. We've evaluated from the perspective of performance. Does it perform well enough? So what's left for us at this point? Well, we're building increasing confidence in our release candidate. But one thing that we don't know yet is that it works with production data. So maybe we should test that we can cope with our data. If we've got a database associated with our thing, or any form of persistence between interactions of our system in production, we probably want to check that we're able to migrate that data to new versions. We want to be able to evolve and develop our data stores as well as the rest of our software. So we want to evaluate that we can migrate the data. In the example that this is based on, what we used to do is that we used to, our automation would take a cut of production data each morning. It would anonymize that data, because we were a finance institution and we weren't allowed to have real customer data in test environments. It would anonymize that data and copy it across to a test environment. And then each release candidate that came through our deployment pipeline would work with that data, including migrating any changes to our specification of our data structures as part of our automated deployment, and then run a series of high-level smoke tests against the system just to test that it was sane at the end of it. At this point, there's really nothing left for us to test. This release candidate, if it's passed all of these tests, we can have a fairly high level of confidence that this release candidate is going to be successful in production. Now, remember what I said earlier. We can never prove that this release candidate is good. We can never have enough tests. However many tests we have, we can never have enough to be certain that it is good. But if we've got a high level of testing, the probability that it's going to be successful in production is higher. And as long as none of those tests are failing, we know as much as we can know. Organizations that practice this kind of approach do vastly more testing than any level of human regression testing. as a rule, as a rough guideline to just try and paint this picture. The organization that this example was based on, as I said, finance institution. We were building an exchange for trading currencies. In the commit stage, when I left, we were running in the order of about 30,000 unit tests. In the acceptance test stage, we were running somewhere between 15 and 20,000 automated acceptance tests, interacting with the system from the perspective of the user. Manual testing was kind of ad hoc as we were developing stories as we went along. The performance tests combined, we were probably talking about in the order of a couple of thousand performance tests. And data migration tests, there were a handful of a few tens of data migration tests that were run. This whole mechanism, this whole approach is called a deployment pipeline. And as I've kind of alluded to, you'll slightly tailor the deployment pipeline to meet the needs of your project. You may not need so much performance testing as we did in our version. You may need more scalability testing. We also did resilience testing as part of our acceptance testing. So we would selectively kill bits of the system and see that the system was still intact and hadn't lost any data, those kinds of things. If you work in a regulated environment like finance industry or gambling or medicine, those sorts of areas, then you can imagine, think for a minute about this as a software system. Think about this mechanism, this deployment pipeline as a software system. You can't really build this software system without having pretty much perfect traceability from the point at which an idea comes in to the point at which you deploy this into production. You can audit through automation, almost as a side effect of normal working practice, every aspect. You can make a note of who committed what changes. If you link to your story management system, you can link who decided that this was a good idea in the first place, who worked on it at each stage. You can audit the tests that were run against it, which manual testers checked this release candidate out and deployed it, and what tests they ran against it, and what the results of the performance tests were, who authorized, who clicked the button to say to deploy this into production. This is what regulators in highly regulated industries are really looking for. My experience of working in those industries with this sort of approach is that at first regulators may be a little wary because they're unfamiliar with the idea, and they're saying, you want to deploy how many times? That's a really scary idea. And then when you explain the rigor of this approach, they want more of it, and they start recommending this to other people as approaches to doing this. This is the way that regulated industries are moving in terms of defining what software quality really is. So in my work as a consultant and working with organizations to do this, one of the pushbacks that I sometimes get is, okay, that sounds like a great idea for small projects, but it can't possibly scale. And for that, my argument is the Google build process. Google have taken the unusual choice of putting all of their software in a single monolithic repository. All of their different projects are all in a shared repository. So if you commit a change to any of Google's software, it evaluates that change alongside all of the rest of Google's software. This data is a little bit out of date now, but at the time when I collected the data, there were roughly 60 million builds a year, and a number that was growing exponentially, 100 million lines of code. There were more than 20 commits a minute, and they were running 100 million test cases per day. So if your software project is bigger than that, maybe continuous delivery doesn't scale, because this is the biggest example that we've got so far. But if you find that project, come and talk to me, because I'd be interested to find out. The other pushback that I sometimes get is, this is way too risky. You're talking about releasing changes all of the time. You're really focusing on release as an almost constant approach. And my pushback for that is the Amazon build process. My guess is that many of you, probably all of you that are listening to this, have used Amazon in the last week or two. Most people, it's that popular a website, obviously. And a question I just pose you to ponder on for a minute: what version did you use? That's a stupid question, because you don't know and you don't care. And you're right not to know and not to care. And one of the reasons for that is because the mean time between deployments for the Amazon system is once every 11.6 seconds. Once every 11.6 seconds, a release is being pushed out to more than, on average, 10,000 hosts. Since adopting this approach, Amazon have seen a 75% reduction in the outages triggered by deployment. They've seen a 90% reduction in the time spent resolving problems with deployment. And less than 1 in 1,000 deployments cause any problems. And when they do, they now have the facility to instantaneously roll back the change. Remember what I said about if we're releasing frequently, each change is small and simpler to reason about. The last pushback that I often get is, okay, so this may work for simple websites like Amazon and Google, but my technology is way too complex. And my example for this is the HP LaserJet firmware team. So the HP Laser, this is the firmware that operates all HP LaserJet devices: scanners, printers, used to be fax machines, all sorts of devices. And they were in a pretty poor state. So in 2008, they were spending 5% of their global development effort on what they called innovation, what you and I would call any new features at all. The rest of their development effort was spent in integrating code, porting code. 25% of their global development effort, 5 times the amount of time they spent on doing new stuff, was spent porting code. They did 25% of their effort on product support, which says that they had a quality problem. The reason they spent so much time porting code was because each device, they had one code base for all of the HP LaserJet firmware, but each device had its own branch. So every time there was a new feature, they then had to go and port that feature to a slightly different version of the software for all of the other devices. They got to the stage where they had a backlog of changes that was, I think, if I remember correctly, more than 5 years long. The business had got to the point where they'd literally stopped asking for any new features because they knew they would never get them. At which point, the management and the development teams decided that they needed to stop and pause and think again. And they went through a very similar kind of mental exercise to the one that I've just guided you through. They said, so what is it we really want? We want to get changes out to our users as quickly and as efficiently as possible. And what does that take? It takes us being more scientifically rigorous, more empirical. What does that take? It takes more automation and all of these things. And so they started adopting the sorts of practices that I've been talking about. At the end of adopting those practices, it took them a few years, as you can see from this slide, but by the end, they were now spending 40% of their total development effort on doing new things. A nearly 10 times improvement on what they were doing before. If you look at the work that they were doing in other areas, though, it's kind of interesting. So they spend an awful lot of time working on automated testing, writing tests, automated testing, continuous integration, improving tools. These are really different sorts of activities to what was going on in 2008. But the bottom line is that they were creating higher quality software more quickly and more efficiently. This is summed up in this book that I show here, A Practical Approach to Large-Scale Agile Development by Gary Groover and several other people. The summary from this book says that overall their development costs were reduced by 40%, while increasing the number of programs by 140%. Development costs per program were down by 70%. Resources driving innovation was up by a factor of 5. So there's been a bottom line improvement. It's my argument that whether you adopt continuous delivery or not, it will impact on you. Continuous delivery changes the economics of software development. I believe that what we are learning is that we're learning what software engineering really is, and it's something different to what we expected it to be. Fascinatingly, there's fairly recent research, peer-reviewed research, that for the first time in the history of the software industry shows a bottom line advantage to organizations that practice a particular approach to software development. If you're practicing the principles of continuous delivery and DevOps, you are going to make the organization that you work in is likely to make more money than organizations that don't. So I believe that continuous delivery is going to impact on you. I believe that whether your organization adopts it or not, it's going to have an impact. If you adopt it, you're going to create higher quality software more effectively, and you're going to please your users better. You're going to change your relationship with your users. If you don't adopt it, then your competitors will, and when they do, they will beat you in the marketplace because they'll be pleasing your users. Here's just kind of a summary of some of that data. So again, I just want to reinforce the point. This is peer-reviewed research. So high-performing IT organizations, that is, IT organizations employing practices like continuous delivery and DevOps, are twice as likely to exceed profitability, market share, and productivity goals. They're 50% higher market cap growth over 3 years. And from a different report, 66% report that software quality has improved. And what defines a high-performing IT organization? IT performance and strong DevOps practices. Read DevOps continuous delivery. Organizational culture and climate for learning. And the #1 predictor of all of these things is job satisfaction in the people that work in these organizations. This is not only a more productive, higher quality, more rational, more empirical, dare I say it, more scientific approach to software engineering, but it's also more fun. It takes away some of the stresses. It empowers us to be more creative and come up with higher quality, more interesting solutions to problems. So who practices continuous delivery? There are some. This is just a tiny fraction of organizations that are publicly talking about the adoption and the use of continuous delivery as a practice. And there are organizations here that you would kind of expect to see: Google and Amazon, Stack Overflow, those sorts of organizations, Flickr, Netflix are kind of well known in this space. But there are other organizations, financial institutions, the LMAX Exchange where I used to work, the New York Times, Volvo, developing the software that's moving them in the direction of fully autonomous trucks, are using continuous delivery in the development and testing of their systems. They can do testing in a couple of hours that used to literally take them months before adopting these approaches. NASA, as a science nerd, I was particularly delighted to hear this. The Curiosity rover, that amazing piece of engineering that was lowered by a crane supported by a rocket-powered sled that had entered the atmosphere of Mars, onto the surface of Mars, the software that did all of that was written using continuous delivery practices by NASA. SAP, to my mind, kind of the definition of a legacy systems, but SAP are talking and publishing about the adoption of continuous delivery in some of their for some of their software, and reporting significant improvements in productivity and the quality of their software. That's the conclusion of my talk. Thank you very much indeed for your time. If there are any questions, I'll be happy to take them there. If you'd like to enter any questions in the chat room for the webinar. Pavel, thank you for the thanks. Thank you. That's very kind. If there are no questions, I would like to say thank you very much indeed for your time. I'm sorry about the technical difficulties at the outset, and I hope you have an excellent weekend. Thank you, Mai.